Welcome to this video lesson. We are going to be looking at how forces in physics can be represented as vectors. Some of the prior knowledge that will be useful for this lesson would be components of a vector, geometric operation, and magnitude of a vector. We're going to start off with an example of two people putting a force on a box. So the person one is putting a force 12 newtons to the right, and the second person is pulling with a force of 15 newton to the right. By definition, net force or the resultant force is a combination of all external forces acting on an object, in this case the object being our box. In this particular example, the forces are only acting in one dimension. We're going to take right to be positive, and the net external force acting on our object is 12 newton from force 1 or person 1 and 15 newton from person 2. And the combination of these forces will be 27 newton. And since we've taken right to be positive and our final answer was positive, that means the total resultant force also acts in the right direction. For the next example, we're going to start talking about two-dimensional forces, and we're going to have a boat or a bigger boat which is attached to two smaller boats, and those two smaller boats are going to be pulling the bigger boat at 300 newton with an angle of 30 degrees to the horizontal. When we're dealing with two-dimensional forces, we need to break them down into their two components, the horizontal component and the vertical component. The horizontal component is usually in the x direction and the vertical component is in the y direction. And usually we choose a coordinate system where we say which direction of x and y are positive. Now we're going to draw the two forces individually, and the first force is 300 newton with an angle of 30 degrees. So the y component is going to be the opposite side, so that's 300 sine 30, and the x component is going to be the adjacent side, which is 300 cos 30. The other force has very similar components. The x component is adjacent, so that's 300 cos 30, and the y component is opposite, so it's 300 times sine 30. Now for the x direction, we're going to take right to be positive. That's same as our coordinate system, so f net x is going to be the x component of the pink force, 300 cos 30, plus the x component of the purple force, which is 300 cos 30, and when we add them up, we get approximately 519.62 newtons. Now, since we've taken right to be positive, that means our final answer will also be in the right direction. If it was negative, that means it would be 519 to the left, but since it's positive, it's just to the right. The direction of force also corresponds to the direction of acceleration, and in this case, that means that our object will be accelerating towards the right. Now, for the y direction, we're going to take up to be positive, and the y component of the first force acts upwards, so that's going to be positive 300 sine 30, and the y component of the second force acts downwards, which is opposite to what we've chosen to be positive, so that's negative 300 sine 30. When we add them up, we get 0 newton, direction up, and when it's 0 newton, that means the object doesn't have an external force, net external force, and therefore it does not have an acceleration either. Let's talk about a few definitions. Acceleration is the rate of change of velocity, meaning velocity and speed needs to change for us to have acceleration with respect to time. And in most cases, when the net force is equal to 0, acceleration also equals to 0, meaning that objects at rest will remain at rest, meaning they're not going to change their speed, and objects at constant velocity will also remain at a constant velocity because they're not going to change their speed. And this is known as the first law of motion. Now, one of the big applications of this then is objects at rest. So if an object is at rest and remains at rest, that means the net external force acting on it must equal to 0. Final definition for today, we're not going to go into too much detail about this, but force of gravity, in the most basics, it acts towards a planet and is calculated by this equation. Force of gravity is equal to mass times gravitational acceleration, where Fg stands for gravitational force, m stands for the mass, and g stands for the gravitational acceleration. Gravitational acceleration around Earth is approximately 9.81. This is a rounded value, that's why I'm using the approximation mark, and we can sometimes use 9.8 or 10 depending on the curriculum. Now let's look at an example. We got a mass that's hanging from the ceiling by a string. It has a mass of 20 kilogram, and we want to figure out the tension on the string. Now, for most questions involving forces, we usually have to follow these steps. The first step is to draw the diagram. In this case, we do have the diagram. The second step is to draw a force diagram acting on the object, showing all the external forces on that object. I personally like to start off by drawing a box around my object and also drawing out Earth. And then I'm going to make that box into a point mass, meaning all of that mass is concentrated into one point. Then I can see that the box is interacting with the string, so the string is going to be pulling it up. We're going to call that a tension force, and the Earth is going to be pulling it down towards it, and that's going to be our gravitational force. Since the box is not interacting with any other forces, those are our only two forces, and then we're going to go to our step 3, which is breaking down the forces into the x and y components, or horizontal and vertical components. In this particular case, we have no force acting in the x or horizontal direction, so our forces are only in the y direction. So then our fourth step is to write the Fnet x and Fnet y equations. First, we're going to choose a positive coordinate system. In this case, forces are only acting in the vertical direction, so we're going to take up to be positive. We could take down to be positive as well. Then we're going to sum all the forces in that direction. So Fnet y is going to equal to the tension force, which is positive because it's going towards the same direction as our coordinate system, minus Fg, because Fg is going in the opposite direction. It is negative. Since we know that in this case our object isn't moving, that means it's at rest or constant velocity, then that means that the net force in the y direction is equal to 0. So therefore we're going to set that equation equal to 0. Our final step is to solve for any missing information. In this case, we will take the right hand side of the equation, so t minus Fg is equal to 0. Rearrange that for t to get Fg, and Fg is mass times gravitational acceleration. That's 20 multiplied by 10. We'll take 10 as our gravitational acceleration, and that gives us 200 newtons in the upward direction. Note that our value here is positive, and since it is going in the up direction, we can see that the direction that we've chosen for our diagram is correct, and intuitively that makes sense. The tension force should be pulling the mass upward. The summary of this lesson is fast forwarded, so if you need to pause and record it, please feel free to do so. And now we're going to look at 2 examples. For the first example, we're going to look at the resultant force, which is created by 2 forces, 20 and 30 newtons, which are acting at an angle of 30 degrees to each other. First, we're going to draw out the forces 30 newtons and 20 newtons, and it doesn't matter which one is going below the other one. The angle between them is 30 degrees. Then we are going to draw them individually and break them down into their components. So the 30 Newton will only have an x component of 30 Newton, and the 20 Newton will have an angle of 30, so its horizontal component is adjacent, taking 20 cos 30, and the y component is the opposite, so it therefore is 20 times sine 30. Next, we're going to write the net force equations in the x direction. So F net x taking right to be positive is equal to 30 plus 20 cos 30, because the x component of the second force is going to the right, and that gives us approximately 47.32. And we're going to take up to be positive for F net y, 0 from the first force, and 20 sine 30 positive for the second force, giving us a total of 10 Newton upwards. Now that we have the 2 components of the net force, the x direction is 47, we're going to draw that and add the 10 Newton going upwards. The resultant force originates from the beginning and terminates at the very end. So to find that angle theta in between, tan theta is equal to the opposite over adjacent. When we calculate all those numbers, we get theta is equal to 11.9 degrees. And to find the magnitude of the net force, we take the square root of the x component squared plus y component squared. And when we do this, we get approximately 48.3656 Newton as our final answer. The net force here is going to be 48.4 Newton, 3 significant figures. And in terms of direction, it's acting towards the 30 degrees and then it's going towards the 20 degrees, so it's 11.9 degrees from the 30 Newton force. For our second example, we have a mass of 10 kilogram which is suspended from a cord that makes an angle of 30 degrees and 45 degrees with respect to the ceiling, and we want to determine the tension in each part of the cord. We're going to draw this out. So we got the ceiling and we got two locations where the cord is attached to, one at an angle of 30 and the other at an angle of 45 degrees, and the mass is attached to that. We'll do some geometry. In this case, if we draw a horizontal line and use the Z pattern, we see that the angle between the mass and the cord is 30 degrees on that side and 45 degrees in the opposite direction. Next step is the force diagram. So we'll draw a box around our object and we'll draw the earth as well. So there's a Fg acting downward towards the earth. There's a tension force pulling it in the right direction and tension 2 which is going to pull it in the left direction. We will now break down all the forces. So for tension 2, it's going 45 degrees with respect to the horizontal. So the x component is going to be the adjacent, so T2 cos 45, and the y component is going to be T2 sine 45. For T1, it's 30 degrees to the horizontal, so adjacent is going to be T1 cos 30, and the opposite is going to be T1 sine 30. And finally, gravitational force will only be acting in the downward direction, so no x component on this one. Now we're going to choose our coordinate system to be positive in the right and upward direction. So if we take right to be positive, f net x is equal to T1 cos 30 because it's going to the right is positive, minus T2 cos 45 because it's going in the left direction, which is opposite to our positive coordinate system, plus 0 because Fg has no component, and that is going to equal to 0 because our mass is at rest. Same procedure for the upward direction. We got f net y is going to equal to the y component of T1, which is T1 sine 30, positive because it acts in the upward direction, plus T2 sine 45, also positive, minus Fg because Fg is going in the opposite direction as our coordinate system. And since the mass is at rest, all of those forces sum up to 0. Now we have most of the information that we need. We know that gravitational force is mass times gravitational acceleration, in this case 10 times 9.81, 98.1 Newton approximately. And our first equation, we get cos 30 times T1 minus cos 45 times T2 is equal to 0. And from our second equation, we get sine 30 times T1 plus sine 45 times T2. I'm going to add Fg to both sides, and I'm going to get equals to 98.1 because Fg is 98.1 newtons. Now we have a system of two equations and two unknowns. T1 is like our x and T2s are like our y. So we can either use a scientific calculator or algebra using elimination or substitution to solve this. In this case, I use the scientific calculator to get T1 is equal to 71.8 Newton and T2, which is approximately 88.0 Newton. They're both approximations because they're rounded values. I have prepared 3 questions for you folks to try out. They are of good quality difficulty, so please try them out. And I will try to post the full solutions to these in a separate video as soon as I can. I hope this video was helpful for you folks to get an understanding about the physics of forces and math of vectors and their combination in a very, very summarized way. Thank you for watching.